We shall be starting a new module called as the solid state physics, and in solid state physics we will be doing a few important topics and that are relevant for these learning of physics or this modern physics that the course aims for. And in this we will talk about, in this lecture we will talk about crystal lattices. In particular we will talk about Wigner-Seitz cell, conventional unit cell, coordination number, some crystal structures, and some specifically some of the the popular structures that we come across, Bravais lattice and some special crystal lattices. Then we will talk about reciprocal lattice, Miller indices, and how these crystal structures are determined using X-ray diffraction. Then we talk about BraggS law and an alternate formalism which is known as the von Lohe formalism. We will talk about structure factors and the selection rules which are specific to the lattices, the crystal lattices, the type of crystal lattice that which order or which a peak will survive and which peak will not. That is given by the selection rules. So, we will talk about that. So, let us start with this definition of unit cell. So, it is unit cell is the repetitive arrangement of the smallest unit which is capable of building up the entire crystal structure. So, if you take one unit cell and then replicate it in all directions, say x direction, y direction and z direction, that would give you the entire crystal structure. That is called as a unit cell, the smallest one of that. For example, these unit cells are shown by these the corners of these red dots. So, each of them is a unit cell. So, that when translated in along the coordinate axis, they produce the entire crystal structure, and that is what is shown in all of A, B and C. So, these are a variety of these unit cells that are there, and this figure is taken from this website. A primitive cell, on the other hand, is a unit cell that contains only one lattice point. So, that is the smallest possible structure of a crystal lattice. If you take an example, if there is a lattice point that lies at the edge of a unit cell, then it is shared by another adjacent similar unit cell, then it is only counted half. Accordingly, a lattice point located at the corner of a cube, we are talking about in 3 dimension, is shared by 8 such cubes. So, we talk about a primitive unit cell or a primitive cell. A primitive cell is a unit cell that contains only one lattice point, and it is a smallest possible structure of a crystal lattice. Now, suppose there is a lattice point that lies at the edge of a cell, we just talk about say 2 dimensions, and is now shared by say with another similar unit cell, then it is only counted half. So, one point is being shared by 2 unit cells and it is counted half. So, for example, in 3D if you talk about a cube, lattice point that is lying at the corner of the cube is actually shared by 8 such cubes, and so it will be counted as 1/8. Okay. So, let us talk about a Wigner-Seitz cell. These are special primitive cells which are known as a Wigner-Seitz cell, and the primitive unit cell of a Bravais lattice is called as a Wigner-Seitz cell. And how can it be constructed? It can be constructed by taking a particular point and join with all other nearest neighboring points, and then you take a perpendicular bisector of all these connecting lines, and the volume it encloses is called as a Wigner-Seitz cell. Okay. So, that is the definition of Wigner-Seitz cell. Let us just go over for clarity once more. So, you take a particular point and then you join with all other neighboring points that are nearest neighbors, and then you draw perpendicular bisector, and these perpendicular bisectors from all sides will enclose a volume, and that volume is what we know as the Wigner-Seitz cell. So, there are 14 Bravais lattices and 230 non-Bravais lattices. So, some of these are pure information. So, let us see this more carefully, I mean this or rather construction of a Wigner-Seitz cell. So, you see that there is a red point that you see here, and that is connected to all its neighbors in say a honeycomb kind of lattice, and these are the 6 neighbors that you see there. So, they are connected. Now, this is in 2D. So, you take the perpendicular bisector of each of these lines and the volume that it encloses, in this case it is a area, this is a Wigner size cell. Okay. What are reciprocal lattice vectors? In fact, this is an important concept and which pervades all of solid state physics to be particular. We go to a Fourier space. Sometimes we prefer talking about Fourier space because the Fourier space is more convenient to talk about. That is because the real space has a finite extent. You cannot really consider an infinite real space lattice. You can always consider that, visualize that, but for any calculations we have to think of extending it in all directions from minus infinity to plus infinity. Whereas, in the reciprocal space or in the Fourier space, it is much easier to talk about the k vectors, and these the k vectors are defined as k equal to these wave vectors. These are k equal to 2 pi over lambda. So, in principle these infiniteness of the space is encoded in the k space, where the smallest k vectors actually correspond to large lambda, very large lambda, infinite lambda, which means that it can accommodate wavelengths which are, or waves which have a very large wavelengths. So, we define these unit cells. So, these A1, A2, A3 are the primitive vectors of the crystal lattice in real space. So, you can write that in real space, and let us define B1, B2, B3 are the primitive vectors of the reciprocal space. Okay. And we have this equation 1. And this each vector, that is B1, B2, B3 is orthogonal to these A1, A2, A3, and then they have this relation which are Bi dot Aj equal to 2 pi delta Ij. What it means is that this delta Ij is called as a Kronecker delta, which is equal to 1 for I equal to j and is equal to 0 for I not equal to j, which means that Bi dot Ai would be 2 pi, or Bx dot Ax would be 2 pi, or B1 dot A1 would be 2 pi, and so on. B2 dot A2 will be 2 pi. If you take a dot product or the inner product with B1 and A2, that would be 0. That is what according to this definition. And we also define a reciprocal lattice vector which is formed out of these B vectors. In fact, this reciprocal lattice vector G plays a very important role in our analysis of crystal diffraction or this Bragg diffraction. This is formed out of these B vectors, where G is defined as PB1 plus QB2 plus RB3, where P, Q, R are integers. So, this has all the definitions that we require. We require definitions of the unit cells. Those are like the primitive unit cell, the Wigner size cell, and these direct lattice vectors. So, A1, A2, A3 are also called as a direct lattice vectors. Okay. So, they are the vectors in the real space, and B1, B2, B3 are the vectors, primitive vectors in the reciprocal space. They can be obtained from A's by this these relations of B1 equal to 2 pi into A2 cross A3 divided by A1 dot A2 cross A3, and similarly B2 would be A3 cross A1 divided by the same quantity, and A1 cross A2 for B3 and divided by the quantity, and this is the volume in the real space. That is basically the volume that is made out of the 3 vectors A1, A2, A3 in the real space. And so, if you take this volume to be just a a number, so B1 equal to 2 pi over V A2 cross A3, and that is why this orthogonality relation between the reciprocal lattice vectors and the direct lattice vectors take place. So, let us see certain crystal lattices, or just a generic form for the crystal lattices, and they are cubic, where alpha, beta, gamma are the angles between A, B and C vectors. These are all equal to 90 degree and A equal to B equal to C. That is called as a cubic, the simplest one. And then we have tetragonal systems where A equal to B, but not equal to C. So, two of them equal, but the third one is not equal, yet they are the angles are still 90 degree. Orthorhombic means that none of them are equal. So, we have a a cubic lattice with no sides A not equal to B not equal to C. Angles are still 90 degree, and hexagonal lattice has A equal to B, but not equal to C. Two of the angles are 90 degree, but one is 120 degree. Similarly, we have trigonal where A equal to B equal to C, but the angles are not 90 degree. We have monoclinic, which none of the sides are equal, but we have these alpha equal to gamma equal to 90 and beta to be not to be equal to 120, which means that is the difference between the hexagonal and the monoclinic. Of course, there is also a difference in the direct lattice vectors, which are A. So, remember this A, B, C are the distances or the lattice spacing in the x, y and z directions, and then there are triclinic and so on. So, there are 14 types of unit cell. P is called as a primitive, I is the body centered, F is face centered, C is side centered, which are all written here with P, I, C and so on, and plus you have 7 crystal classes as said earlier, and there are 14 kinds of Bravais lattices. So, this common structures that we encounter there are these cubic structure where it is a body centered cubic, other than this simple cubic which has only 8 atoms at the corners, at the vertices of a cube. This has one more atom at the center, at the body center, so that is called as a body centered cubic. And then there is also a face centered cubic, which every face has at the center of every face. So, this is that face which is side face. Okay. So, that is on the left side face, there is an atom there, there is an atom on the top face that you see here and so on. Okay. So, that is called as a face center. So, all of these 6 faces that we come across, which are front, back, left, right, top, bottom, all 6 have one atom at the center. Then there are hexagonal close packs, which has these kind of a structure, which has a hexagonal structure at the base and at the top, and then there is a triangular structure at the midpoint of this 6-sided figure that you are seeing. So, some of these crystal structures are this NaCl structure and this cesium chloride structure, the diamond structure and the zinc blende structure. So, let me tell you about this Cl structure. You can still see that these are in the NaCl, these are by this closed black dots, and then there are open white dots. The open white dots are called as the sodium plus, and this is Cl minus. And similarly, we have also Cs plus and Cl minus. We have diamond and zinc blende, which have essentially the same structure. And let us just discuss this structure. So, Cl atoms are there in this NaCl at 0, 0, 0, and then it is half, half, 0. We will write it without. So, these are the coordinates of that. And then we have half, 0, half, and we have 0, half, half. So, these are the chlorine atoms. So, chlorine minus is situated there, and the sodium atoms are situated at half, 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 and then we have 0, 0, half, and we have 0, half, 0, and then we have 0, half, 0 and so on. Okay. It is getting a little cluttered, but I think you can figure it out that where these chlorine and the sodium ions are. And for this we have this is a FCC structure, and this is a simple cubic structure. The unit cell is actually simple cubic. So, Cs is at 0, 0, 0, and the Cl minus atoms are at half, half, half. Okay. So, each atom must be viewed as at the center of this cube of atoms of the other kind, that is Cs is in this body centered position for the Cl atoms and so on. Okay. And let us see the diamond structures. So, this the diamond structure, we have the carbon atoms are there in there are so this again this is an FCC structure. This is a simple cubic structure. This is a FCC structure with this carbon atoms at 0, 0, 0 and they are at 1/4, 1/4 and 1/4. Okay. So, these are 2 atoms per unit cell. You see a lot of atoms, but they are shared by other neighboring cubes. And for the zinc sulfide, which has essentially the same structure, we have zinc to be equal to at 0, 0, 0. Then we have it at 0, half, half, and then we have it at half, 0, half, and then we have half, half, 0. And the zinc, and for the sulfur we have 1/4, 1/4, 1/4, and we have 1/4, 3/4, 3/4, and we have 1/3/4, 1/4, 1/4 or 3/4, and then we have 3/4, 3/4, 1/4. Okay. So, that is the zinc and the sulfur atoms are situated. Okay. So, these are some of these common crystal structure, and sodium chloride is nothing but the salt that you eat. And so, how do we know the crystal structures? I mean, how have one found out that how people have determined these crystal structures to be FCC, and with these carbon atoms to be placed there. Carbon, these are all carbon atoms for diamond, whereas zinc sulfide, even though they have the same structure, but they are 2 different atoms there. How do we know all that? And that is known by this X-ray diffraction technique. And before we go on to that, the reason that X-rays are employed to determine the crystal structure is that the wavelength of the X-rays are of the order of angstroms, and this lattice spacing in general are of the order of angstroms as well. So, this forms a natural probe for this determination of the crystal structure, because if you have the wavelength to be too large, then you will be missing the atoms in between, and if you have it too small, then you will not see the atoms where they are located. So, ideally one should use a probe which is of the same order as the measurement that you intend to make. So, you see that there are periodic arrangements of atoms that are placed there, and there is an incident X-ray that falls on these 2 neighboring planes that we show here. These neighboring planes are shown by these green dots or green balls that are there, which are nothing but the lattice point. And then the X-rays are diffracted from these green dots that you see there. And so, the angle that you have is really the angle with the this angle with the normal. And if there is the vertical distance between the planes, that is the green dots is d, then you have these lengths. Let me show it by a color, that these lengths are of of d sin theta. And so, the phase difference or rather the path difference that these diffracted X-rays pick up because of diffracting from different planes of the crystal is nothing but 2d sin theta. So, from this theory of interference, it says that if the path difference becomes 2d sin theta, if it matches with integer times the wavelength of the X-rays or whatever probe you are using, in this particular case it is X-rays. So, lambda is the wavelength of the X-rays. So, if 2d sin theta matches n lambda, where n is certain order, n can be 1 or n can be 2, n is just an integer. If it is integer times lambda, which is the wavelength of the probing wave, then we get constructive interference, and this constructive interference will give a peak in the output. We are just going to see that, and this is known as BraggS law. This is known as BraggS law, and Bragg actually found it in 1913. So, typical interatomic distances are of the order of an angstrom. So, any probe must have wavelength of that order. Okay. So, this is what we have said, and for X-rays we have E equal to the energy of the X-rays is h cross omega, which is nothing but hc over lambda, and if you put in all these values, and these are for lambda equal to 1 angstrom, we have these energies to be equal to some 10 to the power 4 electron volt approximately, and these are characteristic X-rays, and that is why they are suitable for determination of the crystal structure. So, this is a typical setup of this X-ray diffraction. So, X-ray, there is a X-ray source, and it goes through some slit and it falls on the sample, which is a crystal lattice, and from there it falls on a screen, and then of course, the screen is so there is also scattering foil that is there, and from the scattering foil it gets absorbed into the detector, and the detector sends it to PC, your computer, for analysis of data. So, a more simple and schematic diagram would be that there is an X-ray source which comes and falls on the sample, and this gets diffracted, and there is a detector that is placed here on the right, and there is an angle 2 theta. So, that is called as the angle of these or the diffraction angle, and one actually measures or rather plots the intensity of these X-rays that are detected by the detector after being diffracted by this sample, and one usually sees all these peaks that you see there. There are of course some noises, but these prominent peaks are sort of mapped onto certain numbers. As you see, it is a little vague, but it's you can see these 111 and some 200 and all that. So, these are done on some copper oxide, and one gets this X-ray diffraction. It can be done on any sort of crystal structure, and it gives the determination or rather information about what are the coordinates of this copper atom, what are the coordinates of this oxygen, and so on and so forth. Okay. And as you see that it is plotted as a function of 2 theta, where 2 theta is the diffraction angle that you see there on the diagram on the left. Okay. So, the BraggS law gives condition for the constructive interference for the X-rays, which are scattered from different planes of the crystal, which is what we have seen. 2d sin theta equal to n lambda is the BraggS equation, is a fairly simple enough equation for us to analyze. So, you would be knowing everything excepting one parameter, and this d is actually related to the HKL indices, and this d is related to not only the HKL indices which are called as the Miller indices, we are going to see that, but it also depends on the lattice spacing. So, and that depends on crystal lattice as well. Lambda, as we have said, that is a wavelength of the X-rays. D is the interplanar spacing, we have seen that. 2 theta angle of scattering, and theta is the incident angle with respect to normal, n is the order of the pattern. So, how do we find out these Miller indices? So, this intensity of these X-rays, which we will discuss later and along with some selection rules, it depends on how many atoms per unit area are there who are taking part in the scattering process, interplanar spacings and how many planes are involved, etc. And these planes are given by this Miller indices. And what are these Miller indices? These are denoted by HKL, and they are determined by pardon me for the spelling mistake, determined by the following things. So, you determine the intercepts of the plane along the crystallographic axis, okay, in terms of the unit cell dimensions. I will give you example of that. Then take the reciprocals, then clear the fractions, which means that you sort of remove the fractions and then reduce it to the lowest terms such that they are integer and we get these planes. Just now you saw that the output has 1 0 0 2 0 0 and so on and so forth. So, this is how these HKL or the Miller indices are determined. We show some very simple planes. So, there is a cube that you see, and the plane that you see, which is colored in this magenta color, is the 1 1 1 plane. So, what we did is that we found out this the intercepts, which is 1 1 1 along x, y and z directions. Then you make these as fractions in terms of this. So, this is a unit cube. So, the fraction is 1 by 1, 1 by 1 and 1 by 1. So, that becomes 1 1 1. The plane is 1 1 1. So, the crystal plane that you see here, which is painted in this magenta color, is a 1 1 1 plane. For example, see another plane which is has it's only the phase that's coming out. So, this has in the x direction it has a projection, or its distance from the center is 1 unit. Now, this is only the plane that's facing you. So, it has y to be infinity and z to be infinity as well. So, this plane can actually go anywhere from 0 to infinity in the y and z direction. So, we take the reciprocals, it is 1 by 1 and then 1 by infinity, 1 by infinity, we get 1 0 0. So, this again the magenta colored plane that you see is a 1 0 0 plane. Let me show you maybe one or two more, and let me sort of draw it here. So, this is a cube that you have, and let us take this plane, the plane that you see here. Let me do a highlight of this plane. So, this is the plane that we are trying to find out. Okay. And how do we find that out? So, the intercepts are 1 by infinity, 1 by infinity, that is the plane that is at z equal to 1. So, this is the z equal to 1, and this is this is y equal to 1. So, this is y equal to 1. So, your A is in this direction, B is in this direction. So, that is in the direction of B, and this is the C direction. So, this is how we have defined. Okay. So, this is 1 by infinity, 1 by 1 and 1 by infinity again. So, what we do is that we sort of take this 0. So, 1 by infinity is 0 and then is 1, it is 0. So, this is the 0 1 0 plane and so on and so forth. So, if you take a plane which is at the middle of this, so let me draw another one to avoid cluttering on the same. So, we draw another cube that we see here, and once again we call it a B, and we call it a C, and we call it a A. Okay. And suppose this plane that we want to show is basically this plane that is this plane that is there at the kind of A by 2. Okay, so, this is at the middle, and let me again paint that. So, this is the plane that you want to find out, and then this plane is the intercepts are 1 over infinity, 1 over 1 by 2. That is basically the intercepts. So, the inverse of the intercept. So, okay, so we write it just once. So, this 1 by half, and then it is 1 over infinity, and so this is a 0 to 0 plane. Okay. So, the one that you see there is a 0 1 0 plane, and the one that is at the middle. So, this is actually at the middle basically. So, that is at A by 2. I may not have drawn it very well, but this is at the half the distance inside the cube. Okay. All right. So, so that is about this Miller indices. We show a large number of that. So, 0 0 1, is according to the the x, y and z. We have taken different definitions of x, y and z. So, you take the definitions of x, y and z according to your wish, and then you can form these planes, and 1 1 1 we have already seen, and some of these other planes we have seen as well. So, these planes are labeled according to the HKL values. So, now we have gotten this HKL, and we have also wrote down BraggS law, which is 2d sin theta equal to n lambda. D is the perpendicular or rather the distance between two planes and the shortest distance basically. And how are these D's related to HKL, and A is the lattice constant, which if you take a unit cube, then of course A becomes equal to 1, but A is otherwise the distance between nearest neighbor atoms. So, that is A. So, we have 1 over d square equal to h square plus k square plus l square divided by a square for a cubic lattice. For a tetragonal, it is h square plus k square by a square plus l square by c square, and for hexagonal it has more complicated form, and for orthorhombic it has this form. Okay. So, now if we know these d and A, we can find out this HKL indices, and this HKL indices are noted on the these diffraction intensity that you see here. Okay. So, these are the HKL planes which are scattering. So, which plane is giving rise to the scattering and which atoms are there, all those information we can find out. So, we basically can find out the crystal structure of a given lattice. Now, while we formulated BraggS law, there is an important assumption that went in, and this assumption is that we have sectioned the crystal lattice into different lattice planes, and we have looked at the scattering from these planes and these scattered X-rays, they are allowed to interfere, and because they are from different planes, there is a path difference, and this path difference will give rise to a phase difference, and so on and so forth, depending on these path difference to be having integral multiple of lambda, or otherwise we will have a interference pattern or a maxima in the interference pattern, or rather a constructive interference. But so this sectioning of crystal into lattice planes is done. So, that is an approximation, or rather that is a superimposed condition that we have done in order to understand BraggS law. In addition to that, we have assumed that specular reflection. What is meant by specular reflection is like a mirror-like reflection. We saw that figure in which the incident angle is theta with respect to the normal, and we have the scattering angle to be theta as well, and then that gave rise to these extra path difference of these red dotted lines, which are d sin theta and d sin theta, that gave rise to 2d sin theta. So, we have these two are the main assumptions of BraggS law. In fact, there is another formalism, it is called the von Lohe formalism, where no such sectioning of the crystal needs to be done. Okay. And we just consider a crystal to be composed of identical lattice points which are separated by a lattice vector r, where lattice vector r is nothing but some p a1 plus q a2 plus r a3, where p, q, r are integers. They also can be written as n1, n2, n3 or nml and so on and so forth. Okay. So, that is the definition. So, that is the basically when you go from one lattice point to another, it constructs the entire crystal, and so the crystal is just simply we take 2 points which are at a distance r apart, and we do not section it into planes, and neither specular reflection is assumed. Okay. So, each lattice point, instead of like mirror, it scatters uniformly in all directions, not mirror like, right. If you stand in front of a mirror, then only you can see yourself, but if you see the mirror from a side, you do not see your image on the mirror, and that is because the mirror only gives rise to a kind of reflection where the incident angle and the reflected angle would be same. So, there is no mirror like reflection that you see, and that is not required in this particular case. And the diffraction peaks are observed when the scattered radiation that interferes constructively. That of course remains unchanged because you need to have a scattering condition, but the main two assumptions, that is sectioning of the crystals into lattice planes and the specular reflections, these are waved off. So, we draw a picture, we see that there are two lattice planes which are these two ones that you see there. These are at a distance r apart, or these are at a distance d apart. D could be a vector. So, well, d could be r, or we have written that d to be a nearest neighbor distance, and an X-ray comes. Okay. So, this is the direction of the incident X-ray, which is k, and let us call that as the n cap direction, that is unit vector is n cap direction. And there is another X-ray which is coming and falling. X-ray means the X-ray are incidenting on these 2 points, and they are getting scattered in this direction and this direction from these 2 points, and they have k prime. So, that is the wave vector because it is a vector. So, these are the incident X-rays are in the direction of n cap, and the scattered X-rays are in the direction of n cap prime. And what you have is that this distance is like the horizontal distance, which is shown by this underbrace, is the d cos theta prime, which is nothing but a minus d dot n cap dash. So, that is the n cap prime direction. And so, incident X-ray is along n cap direction, wavelength is lambda, k equal to 2 pi over lambda into n cap. Scattered wave direction is n cap, again wavelength does not change. So, that says that your k and k prime, the magnitude of them are equal, both are 2 pi over lambda, but vectorially they are different because n cap points in different directions. And so, d dot n cap minus n cap prime, which is d cos theta plus d cos theta prime, where d is shown there. So, if you actually draw a vector from this one lattice point to another lattice point, we go to this, that vector connecting the two lattice points is equal to d. Okay. So, no sectioning of planes is done, and there is no specular or mirror like reflection has been assumed. So, the condition for constructive interference is that these d dot n cap minus n cap prime, which is basically nothing but the d cos theta plus d cos theta prime, that path difference has to match with m lambda. Here we have written m, m is just an integer, we had written n earlier, but they mean the same thing. So, what we do is that you multiply it by 2 pi both sides, and that gives rise to this equation, which is a d dot k minus k prime, which is equal to 2 pi m. So, k is equal to 2 pi over lambda. So, we multiply it by 2 pi and absorb this lambda on the left hand side. So, these k minus k prime dot r. So, d is nothing but r, basically r is a direct lattice vector, which we have written as d. Why we have written as d to begin with? Because d is arbitrary. D is an arbitrary vector in the real space. It can be a direct lattice vector, which is what we have defined as r. So, because d can be anything, d can be equal to r. So, we have this relation, which is k minus k prime dot r equal to 2 pi m, and that is equivalent in some sense to this condition BraggS law. We will see that, but the condition that gives rise to this constructive interference, and you should see a peak, that is quite different, and the condition is quite stringent, as we shall see in just a short while. So, k minus k prime is a valid reciprocal lattice vector, right, where k is the direction of the incident X-ray and k prime is the direction of the scattered X-ray. And that, if it is not equal to this reciprocal lattice vector, remember the reciprocal lattice vector is defined as, I am again writing, let me write it as n1 b1 plus a n2 b2 plus a n3 b3, where n1, n2, n3 are integers. Now, if this is the condition that exponential I g dot r, if g is a reciprocal lattice vector and r is a direct lattice vector, then this has to be equal to 2 pi m, okay, because this is the condition that comes from this orthogonality of these. So, it comes from this a I dot b j that is equal to 2 pi delta I j. Okay. So, the phase has to be periodic, if g and r, they correspond to the reciprocal lattice vector and the direct lattice vector. So, this tells you that g dot r or something, or this is a stringent condition that the change in wave vector has to match a proper reciprocal lattice vector. This is what is coming, but the condition, if you think about it, X-rays are coming with their own wavelengths and in a given direction. So, the change in the wave vector of the incoming and the outgoing X-ray, or the incident and the scattered X-ray, that has to match exactly the reciprocal lattice vector. If that happens, then only there is a constructive interference and you will get a peak in the output spectrum. So, what by Bragg's law look like a trivial condition, that is 2d sin theta equal to n lambda or m lambda, now it looks quite stringent, because k minus k prime equal to g. If you square this up, and then we can write this k prime square equal to k square plus g square minus 2 k dot g. Now, we know that k prime square equal to k square, because of lambda being same, that is the elastic scattering. Then we have this condition that comes out, which is g square equal to 2 k dot g. So, that is actually the von Lohe formalism that it says. Okay. So, if we putting it in another form, is that the half of the reciprocal lattice vector, which is g over 2, is it should be such that the k is in the direction of the g, or the projection of k in the direction of g has to match exactly with half the reciprocal lattice vector. Geometrically, one can really think of this as, so you have a k coming here and you have a k prime, and it is falling on a crystal plane, and say there is a g that is connecting from the origin to this point there. So, the crystal plane must lie at the perpendicular bisector there. Okay. So, must lie at the middle point for the scattering to give rise to a interference, constructive interference. Okay. This is what is written: the component of the incident wave vector along the reciprocal lattice vector must be half of the length of g. Okay. So, an incident X-ray will satisfy the von Lohe condition if the tip of k lies in a plane that is perpendicular to the bisector. So, that is a perpendicular bisector of a line joining the origin and a reciprocal lattice point. So, what was looking like a very simple condition in Bragg's law, now it looks like that the incident X-ray and the scattered X-ray, their wave vectors have a very intimate relationship with the reciprocal lattice vector of a particular lattice. So, that is why the Bragg diffraction is specific to a given crystal. So, the planes that you see for a simple cubic, you will not be able to see that same plane, say for a HCP structure, okay, or for another diamond structure. And that is the power of this method, that every crystal structure presents you with an output which helps you to determine the exact crystal structure, position of the atoms or the ions, and which planes are involved, and so on and so forth. So, but at the end of the day, there has to be an equivalence between Bragg's law and the von Lohe formalism. Okay. So, we have seen this, that for elastic scattering k equal to k prime. So, the shortest reciprocal vector connecting different planes in the reciprocal space is g0 equal to 2 pi over d. So, the reciprocal lattice vector that we talk about here or in the last slide, there must be some integer times the smallest reciprocal lattice vector. So, this is n g 0. So, g equal to n g 0, which has to be equal to 2 pi by d into n, where d is the spacing between the different planes. So, from the figure, if you see that these are k's direction of k, and that is k prime here, and k has a direction which is in this direction, but so this is taken as a minus k direction, the one that is up there, and then this is the g vector which is equal to k minus k prime, or k prime minus k. Okay. So, it is basically k prime. So, g is equal to k prime plus a minus of k, and this is equal to k prime minus k. So, that is the condition that we have. Now, from this figure you can easily see that g is equal to 2 k sin theta, because this k is a scalar quantity where k is equal to k prime, and if you put in g to be equal to 2 pi by d into n, you get a 2 d sin theta equal to n lambda, which is what you have learned in BraggS law. So, the von Lohe formalism, even though it looks quite stringent and quite sophisticated as well, because it does not make a lot of assumptions which BraggS law did, eventually it gives rise to the same result which it should. Whether you take one formalism or the other, the physical results do not change. Now, we come to this intensity of the Bragg peaks. Okay. And we talk about the structure factor, we talk about the selection rules, and whether all planes will be there for a given crystal structure, or there are certain planes that are missing, and how do we a priori know that which peaks we would not see for a given crystal structure. Say for example, for FCC, are we going to see all peaks as we have seen it for simple cubic? If that is true, then there is no way of determining that which one is simple cubic and which one is FCC. So, there has to be certain other condition that should come in, and here as we have said earlier, that there is a diffraction intensity also forms a role, basically the y axis or the height of a peak and so on. Okay. And so, as I said that a simple cubic lattice should be distinct from HCP lattice or from a zinc blende structure and so on. So, suppose there is a Bragg peak that is associated with a change in wave vector g, okay, which is the Bragg's condition or the von Lohe condition. The path difference between the rays scattered at two locations di and dj, where di and dj are the locations of two atoms in the crystal lattice, then the difference is path difference is g dot di minus dj. So, if this is the path difference, the phase difference is given by exponential I g dot di minus dj. So, that is the phase difference, and this phase difference we know that it has to match certain multiples of lambda. So, if you have all these crystal lattice or lattice points that are placed at D1, D2, D3 from some chosen origin, where D1 is a vector that connects the first atom, D2 is the second atom, and D3 is the third atom and so on. So, then they have these the phases of the scattered rays will be in the ratios of these phases, which are exponential I g dot d1 and I g dot d2 and so on and so forth. Okay. So, a scattered X-ray will pick up all these phases, and we will get what is called as a geometric structure factor will be expressed in terms of sum of all these phases that would come. Okay. So, the intensity of the Bragg peak would be proportional to this S g mod square, and that will be the height of the output spectrum in a X-ray diffraction experiment. Okay. Now, the total scattering amplitude would be proportional to these sum over or integration of dV nr exponential I k minus k prime dot r. Once again, k and k prime are these incident and scattered X-ray wave vectors. N is basically an electronic concentration that lies within a small volume dV, okay, and k minus k prime equal to delta k, which has to be equal to g, the proper reciprocal lattice vector. So, if you put that there, so your delta k equal to g is put in this. So, this is equal to g, and we have nr exponential minus g dot r. Now, because of the crystal structure, we have these densities of the electron densities would be repeating, okay, in a periodic fashion. So, as you go from some point r with respect to some chosen origin, you go to r plus capital R, where capital R is the direct lattice vector, you see the same density there. So, this we can write it that we integrate over all the cells, and then there is a sum over r, and its nr is equal to which is nr plus r, and its exponential minus g dot r, which is equal to so the n we do these, there are n of this direct lattice vectors. So, this sum over r is now replaced by this n. So, we have these total scattering amplitude, which is f of g, which is equal to n into integral over some unit cell into dv nr exponential minus I g dot r. So, that is exactly what we write once again, and that is nothing but n s g, where s g is what we have defined in the last slide. Okay, so, s g is called as a geometric structure factor, and we will have to eventually find the intensity of the Bragg peak, which is proportional to s g square. So, s g is nothing but this these n j r minus r j sum over j and these exponential minus I g dot r, and we write that in terms of so r minus r j to be some vector called rho, and we take this minus I g dot r j to be outside, and then it is the integral is dv n j rho exponential minus g dot rho, where rho is nothing but r minus r j. R is a general lattice point, that is any arbitrary lattice point with respect to some origin is written as r, and r j is the individual lattice points. So, rho is equal to r minus r j. So, this helps us in defining the atomic form factor, and which is defined as this dv n j rho exponential minus I g dot rho. So, s j becomes equal to this f g here and sum over j and exponential minus g dot r j, and g is of course different for different lattice geometries. So, s j becomes equal to f j into exponential minus 2 pi I p x j q y j and z r j, and then there is a sum over j. So, you have say 2 atoms per unit cell, you will have to sum over 2 terms, where x j, y j and z j are the coordinates of those 2 atoms with respect to some origin. Usually, we choose the origin somewhere at the corner of the lattice or at the middle of the lattice and so on. So, p, q, r of course are integers, and they are nothing but the Miller indices in fact. So, x j, y j and z j are the coordinates of each of those points. And once we know that, let us formulate the selection rules for the FCC and the BCC structures. And we have these BCC has 2 atoms, they are located at the origin and at the body centered place. So, if we put these 2 values for 0 0 0 we get 1, and for half of half we get this factor. Now, you see that there is an exponential minus I pi h plus k plus l, where h plus k plus l is an integer. If it becomes an odd integer, then this 1 will cancel and will get a 0, the structure factor equal to 0, which means that will not give any scattering peak, or there will be no peak in the spectrum because s is equal to 0. And that will happen when h plus k plus l equal to an odd integer. Okay. So, for some values of, so it can't be like 1, 2 and 1 again. So, or 1, 2, 2 and so on. So, 1 plus 2 will become 5, which is an odd integer. So, you will not have any scattering occurring there. So, 1 to 2 plane will not give you any scattering, whereas 1 to 1 plane or 1 1 0 plane will give rise to a scattering, because h plus k plus l equal to even, and then it will give a sort of scattering which is equal to 2 f. Similarly, if we talk about an FCC lattice which has 4 atoms, which are 1 at the origin and there are 4 at there are 3 more at these locations or these coordinates, which are 0 half half, half 0 half and half half 0. And if we put that there, we get a 1 for the 0 0 0, and then each one of them will give rise to one term. So, that tells that you will have for HKL to be all even or all odd. For example, if it is 2 2 0 or 1 1 1, then we get a scattering intensity which is equal to 4f. Okay. So, if 2 are even and 1 is odd, or 1 even 2 odd, we get the scattering to be 0, because these would cancel with 1 and will not get any scattering. So, that is the selection rule, and that is what says that it tells you about the magnitude of the intensity which is there in the y axis, okay, and at least the proportionality it will tell you, and it will tell you that which all planes are capable of scattering X-rays, and then one assigns these HKL indices with respect to the planes and can figure out what the crystal structure is, and then that sort of settles the issue that all these crystal structures that we have talked about are obtained by this X-ray diffraction. So, we will stop here and we will start with something new next class. Thank you.